Hey, today we are going to take a look at the derivative of the natural log function. To define the natural log function, we are going to use an integral. And this should look a little familiar to us. We are defining a function as an antiderivative. So this should look like our second fundamental theorem of calculus. And if we were to take the derivative of natural log, let's see what this is going to be. We're going to talk about this later on, of course. If we were to take the derivative of the natural log of x, we take the derivative of both sides. Remember, so my rule says everywhere there's a t, I replace it with x. So this just becomes 1 over x. And that's our rule for the derivative of the natural log of x. Of course, x does have to be defined to be greater than 0 because we cannot take the natural log of a negative number. You might recall last year from pre-cal, when we're talking about natural log, a natural log is a logarithmic function that is base e. We can write it as log base e of x. And this was named after the Swiss mathematician Leonhard Euler. And by definition, e is a limit problem. And we're actually going to prove this later on this year when we get to series and sequences. One of the most important things to remember, these are our property rules, and this is that the natural log of x and e to the x are inverses. What that means is they can cancel each other out. And you might have saw this last year by saying y is equal to the natural log of x if and only if e to the y equals x. And that is sometimes how we define the natural log of x. So a lot of people always panic about logarithms. Don't stress logs. Logs are kind of tough because we're not used to dealing with them. It's just another way to write the exponent, or what something is actually going to be. So if we say right here, y is the natural log of x, e to the y. We're looking at the exponent of the function. And that's really what a natural log is. We can graph these, so we know that the domain of the natural log of x is from 0 to infinity, and the range is from negative infinity to infinity. In other words, the y-axis is asymptotic. Hence, yx has to be greater than or equal to 0. So our natural log function, and we can do some points here. Hopefully you might remember that the natural log of 1 is 0. And that the natural log of e, the natural log of e is going to be 1. So that gives me a couple of points. 1, 0, and going over to e, up 1, we get this, and because the y is asymptotic, our function will look like this. There's our function right there. Now remember, this is the most important thing to remember about logarithms. The natural log of x, and this is going to help us out throughout the year. The natural log of x is the exponent of the exponential function. That's really all it is. We have these little rules right here. Now, taking a look here, it says the graph of the natural log of x is continuous, increasing in 1 to 1. Well, if it's increasing, that is telling us that the derivative has to be positive. Being 1 to 1, that means it has an inverse, which we saw. And the graph of natural log of x is concave down. We can see that, which means since it is concave down, we know that the second derivative is less than 0. So we know a lot about the derivatives as well. Now there are some properties that we need to know about logs. If a and b are positive and n is rational, then the natural log of 1 is 0. This is just a definition. The natural log of e is also 1 because natural log and e are inverses. They just cancel each other out. That's just a definition. Now the last three are our properties. These are our main properties that we use. And these are what we call the expansion properties. You might remember these from last year. The expansion properties just basically allow us to take a logarithm and expand it. For example, if we take the natural log of a times b, I can write that as the natural log of a plus the natural log of b. And where this comes from, remember, natural log are the exponents of the exponential. If I have two exponentials multiplied together that have the same base, what does that say we can do? We can add the exponents. Remember, the exponents are our logs, right? That's what we said here. Y is the natural log of x. So this, I can add those powers together. I can write this as a to the m plus n. If I'm multiplying, I can add the powers. Multiplying the exponents together, we add their powers together. Likewise with division, the natural log of a over b, I can subtract their powers, and that comes from Algebra 1. If I take a to the m over a to the n, remember, these are the exponents. If we are dividing bases, we subtract the powers. Same thing here. If I divide the same bases, we can subtract the powers. And of course, we have our power of a power rule. This is just saying we can multiply the powers together. Well, we can drop our power. Well, what is this telling me we can do? If I have a to the m to the n, I can write that as a to the m times n. We can multiply those powers together. Remember, the natural log of a is a power, and so is the n. I could just multiply them together. So that's where those properties come from. So let's apply them. Now, I have other videos you can go back and watch and go over these. Maybe I'll put a link there for you if you need it. All right. So how do we write this? We want to expand this as a multiple or difference of logs. So this is the natural log. And the first thing, of course, I notice is I'm dividing. That's my big picture. I'm dividing here. So I can use my property for subtraction. Write this as the natural log of x squared plus 3 squared minus the natural log of, and I'm going to write this as x squared plus 1 to the 1/3. And now it's not done yet because I can still use my power rule to drop the 2's. And you're going to find out why we really like these properties today. It has to do with calculus. Minus 1/3. It's going to make derivatives much easier for us. We'll find out. X squared plus 1. Whoops. Sorry, messed up there. That should be 1/3 natural log of x squared plus 1. There we go. We don't want that. Erase all evidence. And there's our answer. Please do not distribute natural log. You cannot distribute natural log. Don't distribute it. All right. I can write this as a single log by undoing the properties. Well, here I'm going to use my power of power, so I can bring my 2 up. The same thing with the 1/2. And I could write this as the natural log of x plus 3 squared plus the natural log of x minus 2 to the 1/2. And then since I'm adding them, my rule says I can multiply those together, and we wind up with the natural log of x plus 3 squared times x minus 2 to the 1/2. And if you want to write that as a square root symbol, you can. And we probably should put brackets around there to make sure that they're all just with that natural log right there. Very easy to do. All right, so that's a good review of natural logs. Go to video number 2, and we're going to start taking a look at how we apply calculus here. It's really easy. See you then.